Hello, gentlemen. We're going to try to find some more area here today, but this time we're going to try to do it without any error. And our method of doing that is going to be using integration as opposed to the rectangles that we've been using in the past. So I'm going to start today by kind of doing the same thing we did last class period, and that is I'm going to find the area under this curve between x equals 2 and x equals 4. And I'm going to do it by the rectangular method. And I'm going to just make this into two triangles. I'm sorry, two rectangles. And I'm going to do the left side of my rectangles. So my rectangles are going to look like this and that. And if I actually found that area, that first box, whatever the height, right, the height of that first box would actually be whatever the function is when x is 2. So the area of that first box would be f of 2 times, I'm just going to call it delta x. That's what this distance is right here. And in this case right here, my delta x is just 1. But the area of this box right here would be whatever f of 2 is times a delta x, which is 1. And the second box would be whatever f of 3 is, again, by delta x. Now, when I do that, I come up with a pretty good area, but I'm hoping you guys realize it's not a correct area, right? Because there's all this area here that we did not get. It's error. We missed all of that area. So let's do this problem again, but this time let's make our rectangles a little smaller and see what happens. So again, I'm going to find the area between x equals 2 and x equals 4. But this time, rather than make my rectangles have a width of 1, I'm going to make my rectangles have a width of 1/2. My delta x now is going to be 1/2. So when I do this, let's see what it looks like here. So I'm going to have rectangles at 2.5 and 3 and 3.5. So my rectangles are going to look like this. And when I find the area, I'm going to do a very similar thing. I'm going to take f of 2 and multiply it by that delta x. Now over here, delta x was 1. Over here, delta x is 1/2. I made these rectangles thinner. And my next rectangle will be whatever f of 2.5 is times that delta x of 1/2, and so on for all four. Now, what I want you guys to notice, though, is let's take a look at the air. So I've got some air here, some air here, some air here, and some air here. And I want you to kind of visually take a look at all the air over on this right side and look at the air over here on the left side. And the question I have for you is which side is closer to the correct answer? Well, it's this guy over here. He's closer to the right answer. Or we could say less air over here, right? Well, why did that happen? Well, what happened is we made the width of these rectangles smaller. Over here we had a width of 1, over here we had a width of 1/2. Over here I only did 2 rectangles, over here I did 4 rectangles. So what would happen if I did this again, but instead of 4 rectangles, I broke it into 8 rectangles? And I do that again, and now I would even have more rectangles in here. And if you actually looked at it closer, what would happen is some of the air would disappear. We'd actually get rid of little bits of air, like this air right here now is all gone, and this air right here is gone, and this air has been removed, and this air has been removed. So if we broke this into 8 boxes, we would have even less air. Well, what if we broke it into 100 boxes? That would even be less air. What if we broke it into 1,000,000 boxes? That would even be less air. So if we want to get rid of the air, we want a lot of boxes. So how many boxes would we like to go to get rid of all of them? We would like an infinite number of boxes. Now, if we go to an infinite number of boxes, what the heck is happening to the width of each box? What's happening to this delta x? Well, let's look. Delta x was 1 when we had 2 boxes. Delta x was a half when we had 4 boxes. If we actually go down to 8 boxes, the width of these actually only becomes a fourth. If we go to an infinite number of boxes, delta x would be approaching 0. Delta x would be getting really, really small. Well, what do we call a delta x when it's almost 0? We call that dx. So what we're going to do is we're going to do these problems again, but instead of breaking them up into 2 boxes or 4 boxes or even 100 or 1,000,000 boxes, we're going to break them up to an infinite number of boxes. And if we do that, a very interesting thing happens, and that is all of our air starts to disappear. And so what we're going to have is we're going to find the area, right, by summing up all the areas of each box. Now, that's easy to do when you have 2 boxes or 4 boxes or 8 boxes. But if we've got an infinite number of boxes, how in the world are we going to do that? Well, the calculus method of summation is what we call integration. And we were doing some integration problems before. So if you guys remember, when we're finding area, right, what we're doing is we're finding the area of each box. We're finding the height of each box, and we're multiplying it by the width of each box, and then we're summing them up. You know what? What I might do here is, I'm trying to erase. Come on, erase. I'm going to go ahead and I'm still going to call that a sigma. Okay, but if I move over to calculus, the width, which used to be delta x, has become so thin, we now call it dx. And if you guys remember the height, wasn't the height actually whatever the function was at that particular value? So our height is still going to be f of x. But the problem is summation is good when I have a finite number of boxes, but if I have an infinite number of boxes, I don't have the ability to do that. But with calculus we do, we can do the integration. And so if you guys remember, this is what we call doing an antiderivative. We actually could take the antiderivative of something and actually find an answer to it. So let's do an actual problem that we know the answer to, and let's see if we can come up with the right answer. All right, so let's suppose for a moment we have a function f of x equals 3. This is about as easy of a function as we could possibly come up with, right? It would just look like this. When x is 1, f of x is 3. When x is 2, f of x is 3. When x is 3, I mean, it's always 3, right? So let's suppose for a moment here, we want to actually calculate the area right in here. Now, I'm hoping you know right away, right? That area that would have a height of 3 and it has a width of 2. So the correct answer here is 6. All right, I want to try doing this calculus-wise. All right, we're going to break this up not into 2 boxes, not into 4 boxes, but an infinite number of boxes. I'll try to draw one for you here, but I can't really draw it, guys. This is way too big. There's our first box. Okay, So what's the width of that box? Well, the width of that box is a delta x, but it's so small, we're calling it a dx. I've drawn this way too thick, gentlemen. You got to picture that as razor thin, way smaller than that. So the width would be dx, and wouldn't the height be whatever f of x is? And so, and I'm going to sum all these up. I just wrote the same thing over, didn't I? That was kind of silly. Well, f of x, I actually know is 3, so let's substitute that in for f of x right here. And dx is our width, okay? And this now looks like a problem like you guys actually solved before. If you remember, when we do integration, it's the opposite of taking a derivative. We look for our exponent on x. Now, guys, I'm going to put it in here because it's not obvious, right? This is really an x to the 0 because that's just 1. It doesn't appear. So let's actually do our integration, right? We add 1 to the exponent, so it'd be x to the first, and then I divide by 1 because that was my exponent. And if you guys remember, I would actually put that c there. That's how we would actually do the integration. Okay, now we're going to do the integration a little differently this time because part of what we didn't put on was a lower and an upper bound, which are now going to appear right here. And what those are is over where are we in it? Are we looking at the area from 0 to 7? Are we trying to find the area from -1 to 3? No, we're trying to find the area from 1 to 3. So our lowest value of x is 1, and our highest value of x is 3. Okay, now, gentlemen, we integrate, and we've learned how to do that, and we don't want to lose this lower and upper bound. So I just draw a line over here, and I put the 1 there, and I put the 3 there, and I'll show you what to do next. Let's get ourselves a little more space. And so the area here ends up being, let's simplify it, 3x to the first would just be 3x plus c. Okay, and I don't want to lose my 1 and my 3 there. So what I do now is I take the higher value, the 3, and I actually stick it in for x. And so I've got 3 times 3 plus c. And then I take the lower value and I stick that in for x, and I get 3 times 1 plus c. And then I actually take the difference between those two values. So let's see what I got. 3 times 3 is 9 plus c minus 3 times 1 is 3 plus c. And so let's see, 9 minus 3 is 6, and c minus c is 0. The area is actually equal to 6. Hey, that's a good sign. I got the same answer here as I did up here. Integration actually works. Gentlemen, let's do this again, but let's do a harder problem this time. So again, what we're really doing is we're breaking it into an infinite number of rectangles. The width of each rectangle is no longer 1 or a half. It's infinitely small, infinitely thin. We call that small delta x. That's called dx. The height of each rectangle is going to be whatever f of that particular value is. And we're going to look at values of x all the way, in this case, from 1 to 3. And so that's how I'm setting up my problem. Let's do another one that we can actually know the answer to. All right, so let's suppose this time I got a problem that looks like this. Let's say f of x is just a line. So f of x equals 2x plus 3. Okay, and let's say I'm interested in the area between x equals 2 here and x equals 5. So I'm actually trying to find this area right here. Well, let's do it an old-fashioned way. I'm hoping you guys could agree with me that I could just find an area of this square right here. and this rectangle up or triangle up here. And so let's see. This guy right here, let's figure this out. This value right here would be when x is 2, I'd have 2 times 2 is 4, that'd be 7, right? And f of 5 right here would be 2 times 5 is 10 plus 3 is 13. Okay, so this rectangle right here has a height of 7, has a width of 3. That also is 3. And let's see, 7 to 13, that's 6 right there. So this square right here would be an area of 21. I'm just taking 7 times the 3. And the area of this triangle here would be 1/2 base, and the base is 3, times the height, which is 6. And so 6 times 3 is 18, and half of that is 9, and 21 plus my 9. It looks like the correct answer to this is an area of 30. Right? I'm going to do this with the calculus method though. So we're going to break this up in essence into an infinite number of little rectangles that are inside here. I'll draw one for you. Okay, now these rectangles though are so thin that the thinness is dx. So the height is going to be whatever f of x is, right? The width is going to be dx. And since I'm summing up an infinite number of these guys, I'm going to use my calculus summation. And the lowest value of x I'm interested in is 2. I'm going to put that there. The highest value of x I'm interested in is 5. So I'm going to stick that up here. And this is the integration that I'm going to do. Okay, so let's, instead of f of x, let's get what f of x actually is. And over here, remember, f of x is actually 2x plus 3. So I'm going to put my 2x plus 3 in for f of x. And we are off to the races. It is time to integrate. All right, so let's remember this is an x to the first right here, and that's really an x to the 0. And when I integrate, right, I add 1 to the exponent, so that would become 2x squared. I added 1 to the exponent. Then I divide by the exponent. Let's integrate this guy. That's x to the 0. It would become x to the first, right? I just added 1 to the exponent. Then I divide by the exponent, 1. And then I always want to remember that c that's there. And I don't want to lose my values of 2 and 5, so I'm going to stick those out here. All right, and then we take our high value and we stick it in for x. So let's do that. Let's clean this up a little bit here. 2 divided by 2, that'd just be x squared, and that would just be 3x plus c. Let's write it so it looks a lot easier. All right, now let's actually take our large value and stick it in. 5 squared would be 25. 3 times 5 would be 15. Okay, and then remember I put in a minus. There's my high value, and now I'm going to stick in the low value, which is 2. So I put my 2 in here. I get 2 squared is 4. 2 times 3 is 6 plus c. And so now I've got, let's see, this would be 40 plus c minus, this would be 10 plus c. And c minus c drops away, and 40 minus 10 is 30. Hey, good news. We actually got the correct answer yet again. So you might be asking yourself, well, why in the world, do I want to do this, Mr. Bender? You're just making everything hard on me, aren't you? Well, what if the shape is something that we are unable to find the answer? What if the problem looks like this? What if the function is actually, what if f of x equals x squared? That would be a parabola, right? So that'd be a parabola that looks like that. And suppose I said, hey, let's find the area between 1 and 3. Okay, now that, that's not a triangle anymore. I mean, all right, that's a curve there. So there's no way you can come up with an accurate measurement of that area unless you're going to use calculus. And so let's find the area under that curve using calculus. I'm going to break it into an infinite number of rectangles. Each rectangle, though, is so thin, we call its width dx. Its height, right, would be f of x. And we're going to have so many of these to add together, we need to do it in the calculus version. All right, so let's see here. F of x is x squared. So f of x is x squared dx. Let's take a look right here. My low value is 1. My high value is 3. All right, we're off to the races. So x squared, I'm going to integrate that. I need to add 1 to the exponent. So it becomes x cubed. And I divide by the exponent. So it's x cubed plus 3. And let's not forget the c. And then I don't want to lose my values 1 and 3, so we'll stick those there. And what do I do next? I take the high value and I stick it in here, right? So 3 times 3 times 3 is 27. So I have 27 divided by 3 plus c. And then I stick in the low value, which was 1. And so 1 cubed is 1, and so I have 1/3 plus c. So 27 divided by 3 is 9. The c's disappear again, and 9 minus 1/3 would leave me with 8, and 2/3 would be the correct area under here. So gentlemen, it has all come together. We first learned how to integrate, and then we learned how to find area with rectangles, and we did some summations. It turns out integration, gentlemen, has all of those pieces in there. It is a summation. It's not a summation of 10 or 100 things. It's a summation of an infinite number of pieces. Our area, we're doing the same thing. We're taking the height times the width. It's just our width now is so infinitesimally small, all of the air has disappeared. And our width is actually dx. Our height is whatever f of x is. And we're putting the integration in there. Gentlemen, good luck. This is hard stuff, especially when you're trying to teach it via a video. Please remember, I am out on Teams. If you're having any kind of problems, I am more than happy to help you as you go through this. So please let me know what I can do to help you out.